This short video is based on a practitioner survey on the Canadian avalanche size classification, also known as the Destructive Potential Scale or D-Scale. This video is based on a 2014 paper with Rudy Beglinger of Selkirk Mountain Experience and Doug Wilson of the BC Ministry of Transportation and Infrastructure. I'll provide a link to the paper at the end of this video. As part of the process for developing a European classification for avalanche size, a forecaster from the Pyrenees, Ivan Moner, developed a practitioner survey based on photos, maps, and notes of 18 avalanches of varying size. He presented the results at the 2013 ISSW in Grenoble, France. This includes responses from 9 practitioners familiar with the Canadian or Destructive Potential Scale who completed the survey. Since then, another 13 Canadian practitioners have completed the survey. One interesting aspect of the survey is that it asks practitioners to classify each avalanche first using only full sizes, that is, integers like 2, 3, 4, and then a second time in which half sizes were allowed. You'll see the results shortly. Here is one of the avalanches in the survey. It's number 8. The avalanche started up here and stopped down here. This is the map for the same avalanche in the survey. And in the notes, we see the run length, maximum width, average and maximum crown thickness. Last, the notes state that 2 people were killed in the avalanche. This slide shows the results of the practitioner survey for the 18 avalanches, which are numbered along the horizontal axis. The vertical axis shows the distribution of size ratings by the practitioners for each avalanche. In this first part of the survey, practitioners could only use full sizes, that is, integers. The square dot shows the median size. The dark red box shows the middle half of the size ratings. Up to a quarter of the size ratings are shown by the upper whisker, and up to a quarter of the ratings are shown by the lower whisker. Let's look at the ratings for avalanche number 8. Half the respondents called it a size 3, up to 25% rated it a size 2, and up to 25% rated it a size 4. The percentage of respondents who agreed on the size varied from 59% for avalanche number 6 to 91% for avalanche number 17, which was quite small. Overall, the agreement rate averaged 79%. All of the respondents rated the size within plus or minus 1 size for each of the 18 avalanches. Here are the results for the 18 avalanches when practitioners were allowed to use half sizes, such as 3.5. Looking again at avalanche number 8, we see that at least half the respondents rated it a size 3, up to 25% rated it a size 2.5, and up to 25% rated it a size 3.5 or 4. The percentage of respondents who agreed on the size varied from 41% for avalanche number 15 to 77% for avalanche number 1, number 8, number 12, and number 13. Overall, the agreement rate averaged 62%. For the 18 avalanches, 97% of the ratings were within plus or minus 1/2 size. Summarizing the consistency of the ratings, when practitioners could only use full sizes, the agreement rate was 79%, and all the ratings were within plus or minus 1 size. When practitioners were allowed to use half sizes, the agreement rate dropped to 62%. Perhaps surprisingly, 97% of the ratings were within plus or minus a half size. Also, when allowed to use half sizes, practitioners did so for 44%, almost half of their ratings, so half sizes are popular. In the landmark 1981 classification, and again in the Avalanche Handbook, McClung and Scherer argued that there was too much uncertainty to divide the scale into more than 5 levels. In other words, is a size 2.5 really larger than a 2 and smaller than a 3? Or do we use 2.5 when we are waffling between a 2 and a 3? I asked this question at a presentation on this topic in Penticton in May 2014. At that presentation, and since then, a few practitioners have contacted me to say
that they use the half size when they are waffling between two full sizes, especially when looking at an avalanche from a distance. Others say that when they are standing on the deposit with a clear view of the path, they can confidently rate the avalanche to the nearest half size. For some of us, and some ratings, 2.5 means we are uncertain whether it is a size 2 or a size 3. So how might we reduce the uncertainty when rating avalanche size using this classification?
What about those other columns in the definition? Could we use them to reduce uncertainty in classifying avalanche size? Here's part of the definitions, just the rows for size 2 and 3 avalanches. Over the decades, I think I and other practitioners have primarily used the destructive potential, this column, to estimate the size. This is the most subjective column. But if we use the columns for typical deposit mass and run length, could we rate avalanche size more consistency? Typical run length, in the past, I've rarely used this column to help me classify avalanche size, but it could help. What about typical mass? Well, I've not used this often, and when I did, it was mostly for size 4 and 5 avalanches. For deposit mass, we need to estimate deposit volume and density. Since we rarely measure density at depth in a deposit, the geohazards paper includes some plausible values for different sizes of avalanches. Here's a table from the geohazards paper. Using the typical values of density in this column, the paper includes estimate of typical deposit volume for each size of avalanche. The geohazards paper and the companion video to this one suggest that a column for deposit volume could be added to the table for avalanche size. Deposit volume can be estimated from the average depth and area of the deposit. In the past, we've tended to estimate deposit area from the length and width of a rectangle that is about the same area as the deposit. That works, but Rupert Wedgwood recently reminded me that after visiting the deposit, we can also get the area from a polygon drawn in Google Earth Pro. The companion video refers to other scales, all of which use deposit volume, but not mass. Summarizing, the practitioner survey gives us a first estimate of the repeatability between practitioners using full and half sizes. Half sizes are popular. I've argued that this is likely because we, as practitioners, use half sizes when we are sure of which of the two full sizes to use. When I am unsure if it is a size 3 or a size 4, I tend to call it a size 3.5. In my opinion, I and some practitioners have relied too heavily on the column for destructive potential. That is the subjective estimation of potential damage to an object in the track or upper part of the runout zone. The columns for typical run length and typical mass have been, also in my opinion, underutilized. These columns could be used to reduce uncertainty in classifying avalanche size. Also, by adding a column for volume, it could help us estimate mass and hence avalanche size more consistently. Finally, the photos, maps, and notes for the 19 avalanches in the practitioner survey could be used to develop an online training tool. I've talked to a couple of operators who have offered to contribute photos and measurements of avalanches for use in an online training tool, one that could help us more consistently classify avalanche size using a scale that has worked well for us in Canada for the last 33 years. I have referred to the geohazards paper a couple of times. You can press pause to write down the link at the top of the screen, or you can do a web search for avalanche size, Selkirk. That should locate the paper. There's also a companion video on the use of the size classification, especially for large avalanches. It should be on the same site as this video. My thanks to Doug Wilson and Rudy Beglinger, my co-authors on the geohazards paper. Thanks to Ivan Moner, who developed the practitioner survey. Thanks to Rupert Wedgwood for pointing out that Google Earth Pro could help us estimate deposit area and help us classify the size of avalanches. And I'm very grateful to the 22 people who completed the survey. Finally, thanks to the people on the right who, through conversations and anecdotes, have stimulated my interest in the classification of avalanche size. As a member of the ASARC group at the University of Calgary, I'm grateful to the companies and organizations that support the research. Thank you.